Good afternoon, my highly esteemed viewers. Um, Today, I will be taking you on the topic nucleophilic, nucleophilic substitution reaction, nucleophilic substitution reaction. Okay, nucleophilic means nucleus loving. Okay, I like us to remind ourselves of that. Means nucleus loving, and then substitution. It means something is coming to displace another species, displaces another species from a substrate, and of course, you know what a chemical reaction means. Okay, so as we proceed, it's also important to note examples of nucleophiles. Some nucleophiles, most of them have negative charges because something that will love the nucleus that is positive. Remember that the nucleus is positively charged. Okay, something that will love the nucleus must be opposite. So most of them are negatively charged. That's something to watch out for when you're looking at nucleophiles. Another thing to watch out for is the presence of lone pairs. Okay, so you have nucleophiles such as hydroxide ion, um, chloride ion, bromide ion. Those are nucleophiles, and the water molecule is a nucleophile because it has lone pairs of electron, and ammonia is also a nucleophile. So these are examples of nucleophiles, and you should please keep that in mind. A very good example of the substrate that undergoes this kind of reaction are the alkyl halides. Alkyl halides are molecules in which a halogen has replaced a hydrogen in an alkane. So you have methane, for example. If you have methane as an example, you have better still ethane as an example. Ethane. If I replace one of these, if I replace it with a halogen, say Br, this is an alkyl halide. That's how it's named. The one good reason why alkyl halides do this very well is because they usually have this bromine is partially negatively charged. This one is partially positively charged because of the positive center. So this positive center is something that nucleophiles that have this lone pair or that are negatively charged can attack. So that's the reason why alkyl halides are good substrates for this kind of reaction. So what actually happens is that the nucleophile attacks. So using the example that I have up here, I have alkyl, we have ethyl bromide. So this is ethyl bromide. So this is the bromine. And please pay attention because after now, you will be the one to solve the next puzzle. All right. So if I bring in the hydroxide ion here, we'll talk about the solvents later because there is the place of solvent in what we're talking about. But first of all, I want you to understand the principle behind this. All right. So the hydroxide ion. So what happens is the hydroxide ion cannot attack from the front here because the bromide ion has electrons around itself. So that means it's negatively charged, so to say. So, and this one is negatively charged. So there will be electrostatic repulsion if it wants to come from here. Electrostatic repulsion. Okay. Now, also, if you have bulky alkyl groups around here, let's assume you have CH3 here, CH3 here, CH3 here. It will not be able to come from the back because of steric hindrance. But here, there is no steric hindrance. So it can come. So it comes from the back. Okay. This is the one I was referring to. If this, and this, yes, were so big, this is methyl. But if this was also methyl and this was methyl, if this was methyl and this was also methyl, there will be steric hindrance. But now, no steric hindrance. No steric hindrance. Okay, so no steric hindrance. I just want to remove this so that I can do this. So this is partially positive. So this can come from the rear and come and attack. You know, I've told you the reason why it cannot come from where the bromine is. So as it comes from there, what OH is saying is, carbon, I want to form a bond with you. But that would make the bonds around carbon to be more than 4. And that is against tetracovalency of carbon atom. Tetracovalency of carbon atom means that carbon atom can host 4 covalent bonds around itself. That will give it a stable octet structure. But this one that you have brought now, this OH that is trying to, for this nucleophile OH that is trying to form a bond here, is creating the 5th bond. So the halogen would have to leave. Halogens are usually good leaving groups. They usually depart easily. So that leaves. So that moves us to what we have on the next page. Because the OH is coming, and as it's coming at the back, the Br is going. As the OH is coming, the Br is going. You call this a concerted mechanism. Different things happening together at the same time. So the result becomes carbon, then you have your Br, then you have H, and then you have H, and oh, did I say Br? OH is what came in. Br has gone. So you have this. And then the Br will now be there as Br minus. So you have 2 products. What has actually happened is that there has been a substitution, but it's a nucleophilic substitution reaction. And that's actually interesting. It's like what happens on the football field. You remember what happens on the football field? You have 11 players. Okay? If there's a need for substitution, one of the 11 must go out. So you have 4 bonds around carbon. When hydroxide ion needed to come in, the Br had to exit. That is substitution reaction. So that is, this type is called nucleophilic substitution reaction bimolecular. SN2. You must have heard of that before. SN2. It is called SN2 because this is substitution, this is nucleophilic, this is bimolecular. It's called bimolecular because the rate of this reaction, there is an experiment you can set up to establish that. The rate of the reaction between the ethyl bromide and the hydroxide ion, the rate of reaction the rate of this reaction is dependent on the concentration of both of them. So if you alter the concentration of either the hydroxide nucleophile or the alkyl bromide substrate, the rate of reaction will change. So that means both of them have effect on the overall rate of reaction. So that's the reason why we call it bimolecular. If it was only one of them that has effect on the rate of reaction overall, we say that is unimolecular, and that is when you have SN1 reaction. SN1 reaction is another reaction entirely, which we'll discuss in the next video. And now for something that you can play around with, describe, and it's going to help you describe the alkaline hydrolysis of 2-chloropropane. Play around with that, and we'll see in the next class.